Okay, hi guys. We're going to be talking about calculating half-life today. So the first thing we need to do is to define half-life. So the half-life of an element is a measure of time. It's how much time it takes for half of the sample to radioactively decay. And we talked about radioactive decay, so there's three different types of radioactivity that we mentioned, alpha, beta, and gamma particles, and that the purpose of that decay is to make the nucleus more stable. So the half-life is basically a measure of how stable an element is. The longer the half-life, then the longer the time it takes for it to decay. So if it has a longer half-life, it means that the element itself is more stable. And the shorter the half-life, then the less stable it is, because it's really trying to get rid of as many particles as it possibly can in order to get to a more stable configuration. So the shorter the half-life, the less stable the element, or the isotope, okay? So if we were thinking about this in terms of SI units, the SI unit for time is the second, so we could have measurements in seconds, for instance. But you're also going to see half-lives on the orders of days, years, right? Billions of years, okay? And the shorter, again, the half-life, the less stable it is, and the longer the half-life, the more stable it is. So just to give you a sense of this, an element, thorium, we talked about thorium when we were talking about the radioactive decay of uranium. So thorium-230, it's a common isotope of thorium. The half-life of thorium-230 is 80,000 years. Okay, 80,000 years. Whereas radium-223, so remember radium is one of our alkaline earth metals there at the bottom, it's radioactive. Radium-223 is incredibly unstable, and it has a half-life of just days, 11.4 of them to be exact. Okay, so if you were looking at this information about thorium and radium, you would say, okay, well, this thorium has a greater half-life, that means it's more stable, it takes more time for it to radioactively decay, whereas our radium-223 is much faster in that regard. Now in this class, this is more of a conceptual chemistry class, of course, so we're going to talk about calculating half-life. But I don't mean in the sense of plugging things into your calculator necessarily. I just want to talk about it from kind of a conceptual standpoint. So based on the definition, it's the amount of time it takes for half of a sample to radioactively decay. So let's say we have element X, whatever that is, right? There isn't an X on the periodic table, there's an Xe, that's xenon. But if we had an unknown element X and we calculated that the half-life is 6 days. Okay. So we found this new element, it has a half-life of 6 days. Then we could answer questions that look something like this. Okay, so we're calculating how much time it would take to have 1/8 of the original sample. Okay, so we have element X, we have a whole pool of element X, and then over a period of time it's going to radioactively decay, and so I want to know how long it's going to take to have 1/8 of the original sample left over. Okay, does that make sense? So one easy way to set up a problem like this is to start at time 0, or your start time. Okay, at your start you have all of element X, right? You have a whole sample, so let's just call that X because that's what we're dealing with. Okay, now 6 days later, that's our half-life, right? 6 days. After 6 days, the definition of half-life says that I will have half of my original sample. It's the amount of time it takes for half of it to decay. So in 6 days after my start time, I'll have half of the sample left over. In 6 more days, so I added 6 here, I added my half-life, then I'll have half of what I had at the 6-day mark. So I have half of my half, which gives me 1/4 of my original sample. Now the question is asking about 1/8. So if I look and add another half-life, another 6 days here, then now I'm up to 18 days. And now I have a half of my 1/4 of the original sample, so that gives me 1/8 of the original. Okay, so your answer to this question would be, it would take 18 days to have 1/8 of the original sample. Now this is not to say that the sample is going away. It's not disappearing. Matter cannot be created or destroyed because of the law of conservation of mass, but it is transmuting from one element into another, or one isotope into another. Remember that transmutation is changing from one element into another through radioactive decay. Okay, and that's what we defined yesterday in this chapter. Okay, so we can solve questions that look like this. It's asking for, after a certain amount of time, using the half-life information, how much is left over. Okay, we can also use this and solve problems the other way. So let's say that we have element LG. Okay, you named it after me. Thank you for discovering a new element and naming it the Lindsay-Grossium, right? Okay, so if our Lindsay-Grossium has a half-life of 100 years, so just as a concept check here, if it has a half-life of 100 years, your Lindsay-Grossium, how does that compare to your element X in terms of stability, right? These are differences here. Half-life is 6 days versus 100 years. Your Lindsay-Grossium is more stable than your element X, okay? So given this information, okay, if you have a starting sample, however much you started with at the beginning, how much would be left after 500 years? Okay, so we can set this up the same way. So at our start time, we have all of our element, that's all of it. And then after my half-life, 100 years, now I have half, that's my definition. After another 100 years, so I'm adding my half-life here, I'm going to have half of my half, which is 1/4. Another 100 years, half of my 1/4, which gives me 1/8. Another 100 years. Now I have half of my 1/8, so that's going to be 1/16. And then at 500 years, which is what I'm looking for, I'm going to have half of my 16th. So that'll give me 1/32 of my original sample. Okay, so that's going to be the answer to your question here, is how much is left after 500 years. Whatever it is that I started with, I'll have 1/32 of it left over. Okay, again, this is very conceptual. We're not doing a lot of high-level math here, but the concept of half-life is important, so we can use it in these two ways. How much is left after a certain period of time, or like with our element X, how much time would it take to have a certain amount of the sample left over. And these are both practical calculations, although, again, not putting numbers to them as much as trying to understand the concepts. So hopefully this helps, and look over the assignment on Canvas, and let me know if you have any questions.